So by definition, the capacitance, which has a symbol C, is just given by this equation right here. So Q is the max charge. So it's the maximum amount of charge that you can create. So again, if you remember, I showed you an example of so think about this as the negative plate, and this is my positive plate. So how much amount of charge do I create here? The maximum value is just given by this, So we're going to be using this symbol here. So F is called it's the farad. So that's the unit that we use to express. So think about 1 farad simply means that every 1 volt, so every 1 volt is going to generate a total of 1 coulomb of charge on each of these plates. So that's what it means. So 1 farad is one coulomb per voltage, right? So it means that if I were to apply 20 volt, I get 20 coulomb. If I apply 100 volt, I get 100 coulomb of charge. So this is the simplest example of a capacitor that we're going to talk about. This is an example of the parallel plate. So this is just what you see here. Those are two metallic plates. And then you just apply. So this is my body. Now, so in terms of a circuit diagram, we draw this like this. So that's my capacitor. This is my body right here. Now notice that the body has the positive and the negative, right? So this is the symbol for a body. This is positive, this is negative right there. So those two pictures are the same. One of them is the actual device. The second one is just a symbol. So that's how you represent the capacitor. Okay. So let's look at some of the, so notice that we have an area. So this is called the cross-sectional area. This area is A. And then the distance between the two plates is D. And so basically what we're going to do is that once this positive is connected here, we're going to build up positive charges here. And negative charge. So positive charges here and negative charges in the negative plate. So my capacitance is going to depend on the area. It is also going to depend on the distance. So think about the capacitance. It changes with the area. And it changes also with the separation, the distance between the plates. So for example, I can ask you in the exam, can you describe two quantities that you can use to change the capacitance of the system, right? So the area and the separation between the two plates is important. Now I'll skip this quiz, you guys can take a look at that, but let's look at the physics of the problem right here. So the very first thing to remember, again, this comes from Gauss's law. So the electric field between the two plates is given by this equation here. Now remember that sigma is the amount of charge that you have per unit area because this is the surface charge. And so if you plug in everything here, so if you know what the electric field is, you can get the potential difference. The potential difference here is just electric field times distance. And it's given by that equation right there. And then using this, you can write this equation. So from here, so from this equation here, you can say that, so Q is equals to E naught is A over D, all of that times delta D. So notice that we can write this as Q equals to C times delta D, where C is all of this quantity here. And this quantity is called the capacitance. So let me see if I have one example. So I'll do a quick example. So let's, now this equation comes from the fact that, so when you build positive charges on one plate here and negative charges on a different plate, then this will create a uniform electric field. And this electric field is only between the plates. So between. So outside, the electric field is simply equals to 0. All right. So again, I think the main thing here is just, I'm not going to ask you to try to derive any equations here, but I would say just try to understand how to use these equations to solve problems. And so let me show one example here. So let's show one example here. So this is an example. I'm going to solve one example. And in this example, we have something that looks like this. So we have two plates. And this is connected to a body, plus, minus. And we know that when this happens, we're going to build up positive charges here, negative charges. Now the maximum amount of charge here is called Q plus Q, and the maximum amount of charges here is negative Q. So let's suppose that I'm going to give you some numbers here. So let's take, so the area on one of the plate is equals to 6.0 times 10 to the negative 3 squared. And then it tells me that the separation between the plates is 1.0 millimeters, which is equals to 1.0 times 10 to the negative 3 meters. And then we know that this value here, E naught, so E naught has a value of 8.85 times 10 to the negative 12 Coulomb square divided by Newton square. So Coulomb square divided by Newton square, meter square. So what we want to do, so for part A, So for part A, I want to calculate the capacitance. So calculate the capacitance. Calculate capacitance. Part B, calculate the maximum charge. Calculate maximum charge. On each plate. And then part C, I want to calculate the electric field, the magnitude of the electric field between the plates. So let's look at the solution here. So solution, so for part A, the capacitance of the parallel plate is just given by this equation here. So it's A E naught divided by B. So if I substitute everything, I get this value. I get 53 times 10 to the negative 12 farads, which I can write this as 53 PF. So PF is the picofarads. So you have micro. So micro is 10 to the negative 6. What is nano? 9. 10 to the negative 9, and then pico is 10 to the negative 12. All right, so that's part A. So again, as I said, in this section, I think I'm going to focus on you being able to use the equations. I don't think I'm going to ask you to try to derive any equations for the capacitance, all right? But just know how to use the equation to solve problems. So that's part A. Then part B, let's calculate the maximum charge on each of the plates. So notice that I just need to calculate the magnitude, right? Because if there is 1 coulomb on one plate, there is negative 1 coulomb on the other plate. So the two charges, the magnitude of the two charges are the same. So I just need to calculate the magnitude. And I can use this equation here. So Q max is C times delta V. Now, I was going to say that this body has a voltage of 12.0 volts. So that's my delta V. So delta V is the electric potential difference, which is the voltage. So in this case here, if you plug in the values, so you multiply the capacitance by the change in voltage. Again, if you do this calculation correctly, you get 6.4 times negative 10. Therefore, part C is going to ask me to calculate the electric field. So in this case here, so when I calculate the electric field, so we said that when you build positive and negative charge, because this is positive and this is negative, you're going to create an electric field. Now the electric field only exists in between the two plates, right? So it's a uniform electric field. So how do we get electric field? Remember that change in potential. So the potential difference between the two plates. Now, in terms of magnitude, we can calculate this by taking the integral of the electric field. But since the electric field is uniform, you just pull it out of the integral and then you multiply that by the separation between the two plates. And so solving this equation, you get the electric field. So the magnitude of the electric field is given by the electric potential difference between the plates, which is the voltage. You divide by the separation between the two plates. So if you do everything and plug in the values, you're going to end up with this number here. So this would be 1.2 times 10 to the power 4 And this would be in bold and new.